Thank you for joining me today. I will start with this problem to draw the axial force, shear force, and the bending moment. As you remember, we have steps. The first step, I have to figure out the reactions. And I have to be careful about calculating reaction because wrong reactions means wrong diagrams. So this beam looks like we have only one support at A, which is fixed. So at this support, which is fixed, I will have three reactions, one vertical, one horizontal, and moment. I will call the vertical reaction YA, the horizontal reaction XA, the bending moment at this fixed MA. Nothing else. Once you set up your reactions, I'm gonna apply my equilibrium equation. Summation f of x equals 0. Summation f of y equals 0. Summation moment at any point equals 0. My recommendation for your exam, your quiz, your problem, don't write anything below the given beam. I will put my calculations on the left-hand side because under the given beam, I'm gonna draw my diagrams. So be organized. If you apply summation f of x equals 0, looks like we don't have anything except xa. So xa will be 0. This reaction will be 0. If you apply summation f of y equals 0, I have -4, I have -6, I have -8, I have positive ya equals 0. I think I can say ya will be 18 kilonewton. So this reaction equal 18. If you take moment at A, if you assume your counterclockwise rotation is your positive direction, so I think taking moment at A means XA time distance, YA time distance, MA does not need distance. Be careful. MA does not need distance. 8 time distance, 6 time distance, and 4 time distance equals 0. So you are sitting at A. What is the distance between XA and A? 0. YA and A? 0. Your MA does not need distance. The distance between 8 kilonewton and A? 1 meter. The distance between 6 kilonewton and A? 2 meter. The distance between 4 kilonewton and A? 3 meter. I don't care about the direction of this term or this term. Based on my assumption, counterclockwise is my positive, this moment is clockwise, so MA will be negative. 8 times 1 will rotate down, about A will be counterclockwise positive. 6 will be positive, 4 will be positive. All of them, all of these forces going down will rotate about A counterclockwise. The only unknown in this equation is MA, so I can figure out the value of MA. It will be 8 plus 12 plus 12 equal 32. So this moment equal 32, and this direction is correct. Once I set up my reaction and I calculated these reactions, I will draw 3 lines. The first line, 3 reference lines. The first line, I'm gonna draw axial force diagram. The second one, shear force diagram. The third one is bending moment diagram. If you remember, if you would like to draw the axial force diagram, I will look to any force you have parallel to the beam. Since your beam in a horizontal direction, what forces do you have parallel to this direction? The only force or the only reaction is XA. How much? 0. The only force I have is 0. So your axial force will be 0. You have to write something. You have to write 0. That to give me indication that your diagram is 0. We don't have diagram. For shear force diagram, I will play the game. I will move up if the force going up. I will move down if the force going down, but I have to start from left. Here is your left side. So I will start from this end. At this end, I have a vertical force 4 kilonewton going down. So I will go down 4. Then I will move forward. Then I will find another force 6 kilonewton going down. Remember, you are down 4. If you move down more 6, I'm gonna reach you to 10. Then I will move constant. At this position, I have another 8 going down. You are down at 10. If you go down more 8, I'm gonna reach you to 18. Then I will move forward until the end of the beam. You are at 18. Do you have anything at the end of the beam? Yes, I have reaction YA going up. So I will go up. How much? 18. You are down 18. If you go up 18, I'm gonna reach you to 0. If you reach to 0, that means your diagram is correct. This one is negative, this one is negative, this one is negative. If you have any question, just let me know. The last diagram, which is a diagram for bending moment, I need to figure out the value at this position, the value at this position, the value at this position, and the value at this position. So I need to figure out 4 values. Remember and keep in your mind. Remember and keep in your mind. The end of the beam, all the time, your moment equals 0 if there is no given moment. I think this beam, we are not given any moment at the left-hand side at position number 1. The only force we have is 4 kilonewton. It's not a moment. So looks like your value here will be 0. So your value M1 will equal 0. The value of M2, do you remember what was the rule? Equal M1, the previous value for M2, plus area of shear force diagram between 1 and 2. The previous value for M2, which is M1, is 0, plus what is the area of shear force diagram between 1 and 2? Between 1 and 2, we have this shear force diagram, this rectangle, which is -4 times 1. -4 times 1. So the final value will be -4. So I have a value here, -4. The next value, M3. M3 will equal M2, the previous value, which is -4, plus area of shear force diagram between 2 and 3. Between 2 and 3, we have this rectangle, which is 10 times 1 negative. So your value will be -14. So we have another value here, -14. The last value, M4. M4 will equal previous value, which is M3, -14, plus area of shear force diagram between 3 and 4. Between 3 and 4, we have this big rectangle. What is the area of this big rectangle? It's negative 18 by 1. So the final value will be negative 32. Once you put the three values, 32, 14, 4, 0, go ahead and connect between these values by straight lines. You are done. And all of these diagrams are negative diagrams because they are below the reference line. This is called bending moment diagram. So, first step, you have to start with reactions. Put your reactions. Start to draw 3 reference lines, one for axial force, shear force, bending moment. For axial force, we don't have any forces parallel to the beam, 0. Shear force diagram, I have to start from left. If the force going down, go down. If the force going up, go up. Your bending moment diagram, I have to do these calculations based on the shear force diagram. Both of them will help you to figure out the bending moment diagram. Any question? Do you have any question? I will do this example. I'm gonna do this example. So we need also to draw the axial force, shear force, bending moment diagram for the given beam. A is here, is hinge. B is here, it's roller. So first step, I have to start with reactions. Go ahead and set up your reactions. At A, I have 2 reactions, YA and XA. At B, we have only 1 reaction, YB. I will write my 3 equilibrium equations. Summation f of x equals 0. Summation f of y equals 0. Summation moment at any point equals 0. Keep in your mind, for x direction, I have negative 6. I have positive XA. Or vice versa. It's not... 6 is the direction of 6 is positive. The direction of XA is negative. That's fine. No problem. Nothing else. So I can say XA will be 6. And that makes sense. This reaction will be 6 to be in equilibrium with the applied force 6. Looks good. Summation f of y equals 0. We have negative 9. We have positive YA. We have negative 40. We have positive YB equals 0. So I can say YA plus YB equal 49. I'm gonna take moment at point A. I'm gonna assume my clockwise rotation is my positive. So I have everything, XA time distance, YA time distance, 9 kilonewton time distance, 6 kilonewton time distance, 40 kilonewton time distance, YB time distance equals 0. So what is the distance between, I am here at A. What is the distance between XA and A? 0. YA and A? 0. 9 kilonewton at this position and A, 3 meters. 6 kilonewton at this point and A, we don't have vertical distance. The distance for this force must be vertical. We don't have vertical distance between the 2 locations. 40 and A, 6 meters. YB and A, it's 9 meters. I don't care about the direction of this term or this term or this term. 9 times 3 will rotate counterclockwise, it will be negative. 40 times 6 will be clockwise, will be positive. YB times 9 will be counterclockwise, will be negative. The only unknown in this equation is YB, so I can figure out the reaction YB. YB will be 40 times 6 minus 9 times 3 divided by 9. I got 23.67. If you go back here and put YB 23.67, I can say YA will be 25.33. So YA equal 25.33, YB equal 23.67. Let me check it one more time. So 40 times 3 plus yes. These are your reactions. Then just clean up. Then I will draw 3 couples. Reference line, reference line, reference line. One for axial force diagram, one for shear force diagram, and one for bending moment diagram. Do you have forces parallel to the beam? This is a question. Yes or no? Do you have forces parallel to the beam? Guys, this is a question. Do you have any forces parallel to the beam? Yes. So be careful. Be careful about this point. Sometimes your beam may be under the effect of this force, and we have another force here. For example, 8 and 8. Sometimes you have a force here, 8, but the second force is located here, 8. Or sometimes we have this case also. Your force at this location and the second force at this location. What is the main difference between the 3 cases? I would like to highlight this point. The first case, the whole beam under the effect of 2 opposite forces pushing your beam. So if you would like to draw your axial force diagram, the diagram will cover the whole beam, 8, 8, negative, because it's a compression. But if your 2 opposite forces only covering part of the beam, not the whole beam, this part only, this part and is only under the effect of 2 opposite forces pushing this part. So this part only of the beam will be covered with the diagram 8, 8. In this case, your part of the beam, which is under the effect of 2 opposite force, is this part only. So this part only is pushed by the 2 opposite forces. So this part only is under compression 8 and 8 negative. That makes sense? So not all the time, your diagram will cover the whole beam. You have to think which part of the beam under the 2 opposite forces, both of them pushing the beam. So this part of the beam will be under the effect of these 2 forces, 6 kilonewton and 6 kilonewton. The remaining part of the beam will have zero diagram because we don't have anything opposite to each other applying to the rest of the beam. That makes sense? So the rest will be zero, the rest will be zero, but in the first case, the whole beam under the effect of the two opposite force, so the diagram covering the whole beam. Anybody has any question about this point? That makes sense for you? Looks good? Based on the supports at A, we have XA. And the applied force is 6 kilonewton at this point. So the only part of the beam under the effect of two opposite forces is this part. So the only diagram we have for axial force diagram only for this part. The remaining part will be zero. For shear force diagram, I will start from my left. At this left, looks like I have a force going down 9. So I'm gonna go down 9. And then I will move forward until I find YA. YA going down 25.33. So I will go down 25.33. But keep in your mind, you are down at 9. So if you go there up, yes. We keep in your mind, we are not given other forces. That means your reaction will only follow the given force 6 kilonewton. That makes sense? Because if you have something given here, this reaction will be something different. So part of this reaction will opposite to this one, and the other part will opposite to the second one. This is more advanced case. It's outside the scope of this course. We are taking basic course. Maybe we can cover this case if we are taking structure analysis course. It's more advanced. But right now, it's basic. So keep in your mind, your axial force diagram will based on two opposite forces. If the two opposite forces covering the whole beam, the diagram covering the whole beam. If the two opposite forces covering part of the beam, that means this part of the beam will have a diagram and the rest will be zero. Okay. Let's go back. Yes, we are here at 9, down. If you go up YA 25.33, I'm gonna reach to 16.33. Keep moving until you hit 40. I think 40 will bring you down. If you move the down 40 and you are at 16.33, I think I'm gonna reach to 23.67. Keep moving to the end of the beam. You are at 23.67. We have a reaction here, YB going up 23.67. So I'm gonna reach to 0. Once you reach it to 0, looks like we are good. This diagram is negative. This diagram is positive. This diagram is negative. We are ready to start to figure out the bending moment diagram. I will look for what is the value at the beginning of the beam. One moment. What is the value at the beginning of the beam? Then what is the value at this location? Then what is the value at this location? 3. And what is the value at the end of the beam? You should have a reason to get a value at this position. So 1 at the beginning of the beam, 2 at support, 3 at the given concentrated load, 4 the end of the beam. No reason to take any extra points. That makes sense? So what is the value of M1? Keep in your mind, the end of the beam is given without any given moment. So your value at this end will be 0. So M1 will equal 0. So your value at the beginning equals 0. M2 will equal the previous value M1, which is 0, plus area of shear force diagram between 1 and 2. We have this little shear force diagram between 1 and 2. The area of this diagram is negative 9 times 3. So your value will be negative 27. So we have a value here, negative 27. What is the next value? M3. M3 will equal M2, negative 27, plus area of shear force diagram between 2 and 3. What is the area of shear force diagram between 2 and 3? This positive rectangle. What is the area of this positive rectangle? 16.33 times 6. Positive. So the final value will be 71. 71. So this value will be positive. Positive 71. So this value at this position will be positive 71. By the end of the beam, M4 equal previous value, M3 positive 71 plus what is the area of shear force diagram between 3 and 4? This rectangle, which is negative 23.67 times 3. That makes sense. So your value will be negative. This rectangle is negative. 0. So your final value by the end of the beam will be 0. So I have 4 values, 0, 27, 71, positive, and 0. Go ahead and connect between these values with the straight lines. This is called your bending moment diagram. This diagram will be negative below the reference line, and this diagram will be positive above the reference line. Any question?
Excuse me. What does
I'm sorry? Hello?
hello?
Yes.
Hello?
Yes.
I was saying the diagram, right? What does it represents the difference between 27 and 71? Like, what does that mean in terms of what the bar is doing?
The bending moment diagram means a lot of information. There is no meaning the 27 and 71. I don't care about the difference of the values, but the diagram itself, this is more advanced. This beam can be reinforced concrete beam. Your bending moment diagram looks like this. Once your diagram here below the reference line, this reference line represents the center line of the beam. Your bending moment diagram below the reference line, that means your reinforcement steel rebars will be located at the top opposite to the position of this bending moment. Your bending moment diagram here above the reference line, that means your steel rebars will be in the opposite side of the V. So this bending moment diagram will tell you much later in the design process. So it's outside the scope of this course right now, but 71 and 27, I don't care. The only concern, this is steel reinforcement, I'm gonna need lowest number or a small number of steel rebars because the value here is only how much? 27. But the value here is 71, too much. That means I'm gonna use very high number or bigger number of steel rebars. So the values will be reflected or will be transformed to something in the design later. But so far, I don't care about anything. My concern only or only what I need to understand, I have 3 diagrams. These diagrams can help me. These diagrams can help me if I'm giving you, for example, this point, and I'm asking what are the internal forces at this point, capital N, capital V, capital M. What you need to understand only, if you go down, I can tell you what is the value of capital N from this diagram. I can tell you what is the value of capital V from this diagram. I can tell you what is the value of capital M from this diagram. But what is the translation of these diagrams in the real life? You should be aware of design courses. Because these diagrams are very critical to be used in the design. Okay, David?
Thank you, sir.
One more example. This beam with A as a hinge support, B as a roller support, we need to draw the 3 diagrams. Okay, first step, I'm gonna start with reactions. So you need to set up your reactions first. A is a hinge, so I have 2 reactions, XA, YA. B is a roller, so I have reaction 1 reaction at B, YB. Then I'm gonna apply my equilibrium equations. Summation f of x equals 0 looks like XA will be 0. Summation f of y equals 0. I think we have YA positive, YB negative 8, negative 4 equals 0. So YA plus YB will equal 12. We repeated this part many times, how to calculate reactions. I'm gonna take moment at any point. I'm gonna take moment at A equals 0. I'm gonna assume my clockwise rotation is my positive. So you have to list everything. XA time distance, YA time distance, 8 time distance, YB time distance, 4 time distance, and the 20 does not need distance. 20 kilonewton meter at this position does not need distance because it's a moment. So remember, you are sitting at A. So the distance between XA and A is 0, YA and A is 0. 8 kilonewton and A 6 meter. YB and A 12 meter. 4 kilonewton and A 3 times 6, 18 meter. And the 20 does not need distance. This term is 0, this term is 0. 6 times 8 will be clockwise. YB times 12 will be counterclockwise. 4 times 18 will be clockwise. 20 is given, clockwise will be positive. The only unknown in this equation is YB. So the value of this reaction will be 6 times 8 plus 4 times 18 plus 20 divide 12. I got 11.67. If you go back here and put YB 11.67, the value of reaction YA will be positive 0.33. Positive means your direction of this reaction is correct, 0.33, and this reaction equal 11.67, and this reaction equals C. Looks like we are good. I will draw 3 reference lines. One for axial force diagram, one for shear force diagram, and one for bending moment diagram. This is how to solve this kind of problems. Normal force diagram, axial force diagram is the most easy one. The question is very simple. Do you have force or forces parallel to your beam? Looks like your beam is horizontal. The only horizontal force is XA. This reaction equals 0. So we don't have diagram. Axial force diagram is 0. For shear force diagram, I will play the game, but I have to start from my left. At your left, at the beginning of the beam, I have YA going up, so I'm gonna go up a little bit, 0.33. Then I'm gonna move forward until you hit 8. This 8 will move you down until, I think, 7.67. Remember, you are up at 0.33. If you moved it down 8, I'm gonna reach it to 7.67. Keep going until you hit YB going up 11.67. I think I'm gonna reach to 4. If you move forward, by the end of the beam, you are at 4. And we have another force 4 going down. If you moved it down, I'm gonna reach it to 0. If you reach it to 0, that means your diagram will be correct and everything looks good. This is the shear force diagram. For bending moment diagram, I'm looking to figure out what is the value at the beginning of the beam, what is the value of this concentrated load, what is the value at this support, what is the value at the end of the beam. No need to choose another positions. So we have 4 positions. As I mentioned, this course is basic course. I will not make your beam more complicated. This is the case if you are taking another course called structure analysis. This course, structure analysis, is more advanced course related to this topic. That makes sense? So I'm gonna start with M1, M2, M3, and M4. The beginning of the beam, I don't have any given moment. Nothing given at this end, A. So your moment will be 0. M2 equal previous value 0 plus what is the area of shear force diagram between 1 and 2. Between 1 and 2, we have this little rectangle, positive. How much? 0.33 times 6. Your value will be 2, positive 2. So I have a value here, positive 2, and this value is 0. M3 equal previous value, which is M2, positive 2, plus area of shear force diagram between 2 and 3. 2 and 3, we have this little rectangle. This rectangle is negative 7.67 times 6. So your value, I think, will be negative 44. So we have a value here, negative 44. What is the value at the end? M4 equal the previous value, M3, negative 44, plus what is the area of shear force diagram between 3 and 4. 3 and 4, we have this rectangle, which is positive 4 times 6. Positive 4 times 6. This rectangle is positive 4 times 6. So your value will be negative 20. Negative means down. We have a value here 20. So this value is 0. This value is 2. This value is 44 negative. This value is 20 negative. Go ahead and connect between these values by straight line. This is your bending moment diagram. That makes sense? So I don't care about the values. I don't care about the diagram. I don't care about the position of the diagram, positive or negative. But these diagrams will be translated to something else in the design courses. I will do this example, and this is the first example we have uniform distributed load. To be honest with you, this case will not be included in your exam, but this is for your information. If you have uniform distributed load, what will be the case? Okay, let's see. I will start with reactions first. Everything looks good. At A, it's a hinge, so I will have two reactions, YA, XA. For B, I have only one reaction, YB. I will set up my equilibrium equation, summation of X equals 0, summation F of Y equals 0, summation moment at any point equals 0. Keep in your mind, this distributed load will be converted to equivalent. Do you remember that? 15 kilonewton per meter times 3 will give you 45. And the position of this equivalent will be 1.5 from this side and 1.5 from the other side. Nothing new so far. I will apply my equilibrium equation. So summation of X equals 0. I think XA will be 0. Nothing here. This one is nothing. I'm sorry. This one is nothing. We have a mistake here. Okay. Summation F of X equals 0. So XA will be 0. Summation F of Y equals 0. We have positive YA. We have positive YB. Negative 8, negative 45 equals 0. So YA plus YB will equal, I think, 53. Taking a moment at A, I'm going to assume my clockwise rotation is my positive. So XA time distance, YA time distance, A time distance, YB time distance, 45 time distance. So far, so good. You are sitting at A, so the distance between XA and A is 0, YA and A is 0. 8 and A, it's 3 meters. YB and A, it's 5 meters. 45 at this position and A, it will be 6.5 meters. This term will be 0. This one will be 0. 8 times 3 will be positive clockwise. YB will be counterclockwise. This one will be positive clockwise. The only unknown is YB. So the reaction YB will be something like this. (63.3). If you go back here and put YB 63.3, I think YA will be negative 10.3. So keep in your mind, positive reaction for YB means this direction is correct, 63.3. This value, negative value for YA means this direction is not correct. The actual direction is down. This is the correct one. down, down. How much? 10.3. Does that make sense? So be careful about the correct direction of these reactions. Very important. Let's start to draw 3 diagrams. One for axial force diagram, one for shear force diagram, and one for bending moment diagram. The first very simple question, do you have any force parallel to your beam? We have only XA equals 0. So your diagram, axial force diagram, will be 0. For shear force diagram, be careful. For shear force diagram, I'm gonna start from left. At your left, we have a reaction. The correct direction for this reaction is going down. So I'm gonna start down. How much? 10.3. That's fine. The direction of this reaction is down. So I went down 10.3. I moved forward until you have another force coming down 8. You are down at 10.3. If you moved it down more, I'm gonna reach it to 18.3. Then move forward until you reach to YB. I will go up YB equal 63.3. You are down at 18.3. I'm gonna reach it to 45. Then I'm gonna move forward. But right now, you started to enter inside the distributed loop. So I will work normally, but I'm gonna move dotted line. You are going down 45. So I will move down 45 until reach to 0. And then I will move dotted to the end of the beam. At the beginning of the distributed load, which is 45, at the end of the distributed load, which is 0, I'm gonna draw solid line. So this is the protocol if you have uniform distributed load. If you have uniform distributed load, looks like this. That means I will have equivalent. So if you would like to draw your shear force diagram, assume we have a value here. Okay, so I will move dotted inside the distributed load. I have this equivalent moving down, so I'm gonna move down maybe until 0, maybe after 0, maybe before 0, I don't know, based on the case. Then I will move forward to the end of the distributed load. So this is the start of the distributed load. This is the end of the distributed load. I'm gonna draw solid line in between. Sometimes your case, like our case, I moved up here a value. I moved it dotted. When I moved it down due to the equivalent, I found myself to 0. So keep going dotted to the end of the distributed load. So the beginning is here, the end is here. I'm gonna draw solid line like this. So if you have uniform distributed load, we have a protocol. You will move normally, but dotted. By the end, you will draw a solid line between the first point and the last point. If you would like to draw your bending moment diagram, everything will be the same. No change. I need values at the beginning, 1, at this concentrated load, 2, at this position, 3, and the end of the beam, 4. M1 will equal 0. We don't have a value here at the beginning. M2 will equal M1 plus area of shear force diagram between 1 and 2. We have this rectangle, which is negative 10.3 times 3. This length is 3. So your value will be negative 30.9. So we have a value here, negative 30.9. M3 equal previous value M2, negative 30.9 plus area of shear in between. What is the area of shear between 2 and 3? It's a negative 18.3 times 2. Your value will be more negative. Negative 67.5. So I have more negative value here, 67.5. M4 will equal the previous value, negative 67.5, plus area of shear force diagram between the 2 points, 3 and 4. Anybody in this meeting can tell me what is the area of this triangle? It's positive. It will be positive 1/2 times 3 times 45. Do you agree? The area of the triangle, because this shape is triangle, not rectangle like every other examples. So the area of this triangle, 1/2 times base times height. So your value will be 0. So the end is 0. Your value here is negative 67.5. Your value here is negative 30.9. Your value here is 0. Go ahead and connect between these values with a straight line. With a straight line. Except between the two values for the distributed load, I'm gonna draw a curve. This one is curve. And this is the first case we connect between the two values in the bending moment diagram with a curve. Only if you have uniform distributed load. So the shear force diagram looks different. You will have a triangle. And the bending moment diagram looks different because you will have a curve. That makes sense? I can do another example for the case of distributed load quickly. This one. Let's do this one. We are looking to draw there 3 diagrams, and the A is fixed. We have only one support fixed. So it looks like I will have 3 reactions, YA, XA, and MA. I will apply my 3 equilibrium equations. Summation f of x equals 0. Summation f of y equals 0. Summation moment at any point equals 0. Before doing this, keep in your mind and remember, we have uniform distributed load, so I have to convert it to equivalent. 8 times 1.5 will be 12 kilonewton. And this distance will be 0.75. And this distance will be 0.75. If you apply summation f of x equals 0, XA will be 0. If you apply summation f of y equals 0, we have YA, we have negative 12, we have negative 6 equals 0. So YA will be 18. If you take moment at A, if you assume clockwise rotation is your positive, so XA time distance, YA time distance, MA does not need distance, 12 time distance, and 6 time distance equals 0. The distance between XA and A 0, YA and A 0, MA does not need distance, 12 and A 0.75, 6 kilonewton and A 3 meter. This term is 0, this term is 0. based on clockwise rotation is positive. This one is counter, so with this one will be negative. This one will be positive. This one will be positive. The only unknown is your MA. I can find out the value of MA. It will be 27. So this MA equal 27. This reaction equal 18. This reaction equals 0. I will draw 3 reference lines. One for axial force diagram, one for shear force diagram, and one for bending moment diagram. The first question, which is very simple, do you have any force parallel to the beam? We have XA equals 0. Your diagram will be 0. I will move up if the force moving up. I will move down if the force moving down, but I have to start from left. Here is your left. Do you have a force going up or down? Yes, we have 18. So I'm gonna go up 18. I will move forward, but I'm gonna move dotted. Until you have 12, I'm gonna move down 12 to reach to 6, then keep moving to the end of the distributed load. So this is the start of the distributed load. This is the end of the distributed load. I'm gonna draw a solid line in between. Then I'm gonna move forward. We are at 6. I will move solid, normal, because we are outside the distributed load. To the end of the beam, I have another 6 kilonewton going down, so I will move down to 0. This is my shear force diagram. So guys, one more time. In this case, we are given this distributed load with equivalent equal how much? 12. And you have a reaction here, 18. So what I did, I moved up 18. Then move normally, but dotted, because you are inside distributed load. And we have this equivalent going down, so I will go down 12. So I'm gonna reach it to 6. Please move forward, but dotted to the end of the distributed load. Once you get the end of the distributed load, so we have this point and at the end and this point at the beginning. Go ahead and draw solid line in between. This is how to draw shear force diagram for the case of distributed load. And then you can move forward constant, solid, until you have this force going down so you can reach it to 0. You will ask me a good question. What is the reason for that? Keep in your mind, the normal case is you have this distributed load. So we have many arrows. So this reaction will move you up. When you are moving, we have very small arrows. These arrows trying to push you down, down, down. This is the reason why your line is moving down, 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 until you reach it to the end of the distributed load. So how can I do this? I used the equivalent. I used the dotted line to help me to reach out to this shape. Okay? This diagram is positive and this diagram is positive. Your bending moment diagram, I'm looking to figure out what is the bending moment diagram at this location. Number 1, number 2, and number 3. What is the value at M1? What is the value at M2? What is the value at M3? M1, it's not equal 0. M1 will equal 0 if you don't give it anything here. But looks like we have a reaction at the beginning of the beam equal MA equal 27, looks like this. So we already have a moment at this end. And the arrow head of this arrow is down. So your value will be negative 27. Negative means down. If your start of the beam, we are not given anything at this end, your moment will be 0. But in the case you are given a moment as a reaction or given moment, we have to follow this value. And this value will be positive or negative based on where is the head of this arrow. If the head is down, your value will be down and negative. If the head is up, your value will be up and positive. So looks like your value here will be up. Value here, I'm sorry, will be down. It's negative 27. What is the next value? Number M2 equal M1 negative 27 plus area of shear force diagram between the two positions. Keep in your mind, between 1 and 2, we have this area of shear force diagram. It's a trapezoid. It's a trapezoid. This value is 6, this value is 18, and the distance in between is 1.5. So the area of this trapezoid will be 6 plus 18 divide 2 times the distance in between 1.5. Guys, if you have trapezoid like this is A, this is B, this is L, the area of this trapezoid will be A plus B divide 2 times L. And this area is positive. So your moment will be negative 9. So we still negative. The value here is negative 9. What is the value at the end of the beam? M3 equal M2 negative 9 plus area of shear force diagram between 2 and 3. This diagram, which is positive 6 times 1.5. So the value will be 0. So your value here is 0. How to connect between this value and this value? I'm gonna draw straight line. This one is line. But between 9 and 27, I'm gonna draw a curve. This one is a curve. Why? Because you are connecting between two values through a distributed load. So if you have distributed load, your shear looks like line, inclined line, and your bending moment looks like a curve. Does that make sense?